Good morning. I'm very delighted to have such a distinguished audience here today from the departments of chemistry, from chemical engineering, and from the Department of Pharmacy here at the University of Minnesota to give me a chance to talk about organic crystals. This is one of my favorite subjects, and I'm always very happy to have a chance to do this. The talk today is going to be divided into two parts. The first part will be about phase transformations and crystal reactions. And for those of you who think that crystals are always static or stable or are only useful for determining crystal structures, I hope that this first part of the talk will convince you otherwise. The second part of the talk is about crystal growth and morphology, where I will show you different kinds of crystal shapes and colors and sizes and hopefully interest you in the beauty of organic crystal chemistry. The level of the talk is designed to be for a general scientific audience. And those of you who are interested in more detailed scientific information about the examples I'm giving, at the end of each section, I'm going to show you literature references to the systems that I've talked about. The other thing I'd like to mention is that the examples I'm going to be showing you are biased in several ways. First of all, they're mostly examples of crystal systems that I personally have had experience with. And secondly, they're further biased because what I've done is to choose crystals or crystal reactions where there were visual changes that were interesting and recordable. So given that kind of bias, otherwise it's kind of a potpourri of crystal chemistry. All right, the first slide I'm going to show you has to do with schematics. That's not the first slide. Can we back that up on one slide? I think it's okay. If we can just back it up one slide and I'll just continue talking. Here, I can do it here, in fact. Okay, I think we're all right. This first slide shows two different schematics for thinking about how molecules might move when they're in crystals. And the interesting thing about a crystal lattice is that you're starting with molecules that are organized. So I have all of these A molecules lined up in a very nice pattern. And what I'm going to show you today is that there are some ways to make some of those A molecules move, and to move in cooperative fashions and according to mechanisms which are logical. And one possibility is that every other column of A molecules flips upside down. Now that's what we call a phase transformation, because we have a new chemical compound at this point with new properties. It also is actually a chemical reaction. And what we've done is to break intermolecular bonds and remake new intermolecular bonds. So in fact, this is a chemical reaction as well as a phase transformation. A second kind of transformation that takes place is where I'm starting with the same lattice of A molecules, but I'm going to do some kind of a reaction that will cause sigma bonds and intramolecular bonds to change, so that the product will have some B molecules in it. And now we're going to have a product phase that has a mixed A and B molecules in them, and we can talk about this as a chemical transformation. In fact, both schemes are phase transformations and both schemes are chemical transformations. But I'm going to show you examples of both of these today. Now, the first system I'm going to talk about is a very interesting system composed of cyanine and oxonol dyes. And what cyanine dyes are very large cationic organic aromatic systems. Oxonol dyes are similarly large aromatic systems, but they're negatively charged. And so you can form salts between these two. And in one crystal structure that we looked at, the salts are aligned parallel. And that's shown on the left in this slide. And in the other system, the molecules are almost perpendicular to one another. And that's the difference in the crystal structures of these two. And I'll show you in a minute that the crystals of the compound on the right are bright, bright gold crystals, and the crystals of the compound on the left are transparent red crystals. So they're enormous physical and chemical differences that result from these packing pattern differences. And so here is a typical group of crystals that might be isolated from growing cyanine oxinol dyes out of chloroform solution. This is one of the most remarkable crystal systems I have ever worked with. We get 14 different crystal forms. Most of these are polymorphs, some are solvates, and some have different stoichiometric ratios. But we can get out of chloroform a typical set of crystals that looks like this. Here is this bright gold crystal that I told you about. Just looks like a gold mirror. Here are the red crystals that I mentioned a minute ago. And in addition, we have pyramidal crystals. And if you look carefully, and I'll show you some more examples of this in a minute, you can see a phase transformation taking where little black lines are starting to form there where a reaction is actually taking place. In addition, you see several different kinds of red crystals. And while they look very similar to the eye, there are actually 5 different kinds of transparent red needles that we can take out of this sample crystal by crystal and analyze each one independently and show that they're different polymorphs. So it's easy to be tricked by just looking at crystal color and crystal shape and thinking that you have exactly the same compound. Now what I'm going to do is to take a crystal similar to this one, where you see a dark area in the middle and light areas on the side. This one has actually been undergoing a phase transformation, and I'm going to show you over time how the new product phase grows in. So this is actually a fairly true color. It's basically an orange crystal. The reflections you see on the edge are not relevant to the phase transformation. That's just a reflection. But the sort of dark colors that you see starting to grow in here and the purple color up here are actually the product phase. So some kind of a transformation is taking place over a period of time. And here we see more of the product phase growing in. Some purple regions there. Now you see a lot of product phase in the middle, very high contrast. And finally, a crystal that is basically completely transformed. And I'll show you another crystal that has undergone the same kind of transformation just to show you that you see similar effects in different crystals, even though the history of the crystal will determine exactly how that new phase grows in. Now, characteristics that are common to phase transformations in organic crystals include seeing color changes, in this case color changes or new phases growing in at different parts of the crystal. That often happens, although sometimes a new phase will grow in at one end of a crystal and move down the crystal, and we'll see an example of that later. The other characteristic is that at the end of the phase transformation, the crystal is a polycrystalline sample. So if you took an X-ray powder pattern of it, you would see powder lines. You wouldn't see diffraction spots. What that means is that there are a lot of tiny little crystallites of the product that are formed. But interestingly, the product crystal still has mechanical integrity, and you can pick it up and hold it in your hand and it doesn't just fall to pieces. It's very rare that these crystal reactions actually cause crystals to fall to pieces. They are going to change from transparent to opaque, however. That would be a typical change as these polycrystalline domains develop. Now what I'm going to show you is a videotape of the bright gold crystals that I mentioned earlier as they're transforming by losing a molecule of chloroform. They're transforming into a new phase. And I'm going to narrate this videotape as we play it, and it will involve temperature changes. So we actually have this crystal on a hot plate, and we're going to be heating the crystal up and looking for phase transformations very much like the ones that I just showed you here. So let's start that first videotape. All right, so if we watch the crystal on the bottom, this is a very thin, bright gold crystal. We're viewing it in transmitted light, and that's why you don't see the reflective gold color. And the colors that you actually see, it looks sort of purple and orange, those are artifacts. Those are artificial colors. This is actually slightly yellow or slightly red. Now, as we're heating this crystal, you can see, if you look carefully, some small regions that are turning very, very black. And try and keep an eye on those regions. Watch how they grow. Watch where the different product sites are initiated. You can see that the product is forming at different locations on the crystal rather than just starting at one nucleation center and growing throughout the length of the crystal. This is characteristic of some reactions, but they don't always go this way. Something that is very interesting about this transformation, and one reason that we were studying it, is that the color contrast between the product and the starting material is enormous. And I think one reason this is because we're dealing with molecules that have enormous pi systems and have a lot of different possible charge transfer interactions available to them. And I think that's why we're seeing the black color. But what's actually happening here is that chloroform is leaving the solid and we're getting the desolvated product form, which just happens to be very darkly colored. And now you see the reaction is almost complete. If we were to watch several crystals like this, one after another, you would see that the reactions are often initiated at different temperatures, that reaction times, I think that's the end of that tape. Initiation temperatures for reactions depend on crystal history, crystal size. They're often not reproducible within 5 or 10 degrees even. And sometimes even the rates at which these reactions go are not reproducible. So doing kinetics on single crystal reactions is a very difficult business. Okay, I'm going to back this up because what I'd like to show you next is another videotape. And this other videotape is one that was shown to me by Professor David Grant in the College of Pharmacy here at the University of Minnesota. And I had never seen a crystal reaction like this one, and they reported it in such a nice way that I thought it would be worthwhile showing. It's also very similar to what I just showed you a minute ago. I showed you a reaction where chloroform is being evolved during crystal growth. What I'm going to show you with his crystal is how water is being evolved. So he's going to be heating his crystal up about 150 degrees, and at that point in time, water is going to come off. And the difference is that he has his crystal under a layer of silicone oil so that you can see the water collected as bubbles. And it gives a very nice indication of part of the reaction mechanism, the dehydration mechanism here, which we couldn't see when we were looking at the dicrystal reaction. Let's start the next videotape, please. All right, so you can see the crystal here, which is, it is a dicarboxylic acid disodium salt. It has 3 water molecules in the crystal. And at this temperature, about 150 degrees, bubbles of water are just pouring off of the crystal. And you can see them being trapped in the silicone oil. If you watch carefully, you'll see that the crystal is starting to turn opaque at the same time, just like our dicrystal started to turn opaque as the reaction took place. This shows that there's some breakdown in the overall long-range order in the crystal, and you're developing little polycrystalline particles that scatter light. Now, Professor Grant has studied this reaction in some detail, and he knows that at this point in time, 2 moles of water are being lost from the crystal structure. The third mole of water is being retained very tightly, and although I'm not going to show it on the videotape today, if we continued further to heat the temperature up to 170, 180, what you would find is that the crystal would be dormant, and the water would not continue to come off. And then at some point in time later, all of a sudden, water would start to come off very rapidly. This is the third mole of water being released from the crystal. And at that time, that crystal actually does break and crack into little pieces. And that's one of the unusual cases where that actually happens. So here you can visually see two different stages of dehydration. I think this is more exciting than the Super Bowl, frankly. Look at that. That crystal's really smoking. Okay, I think we can stop the tape at that point. Thank you. Okay, so there are two examples of desolvations from crystals, and I've showed you what's happened to the actual crystal. I've showed you a little bit about what happens to the solvent molecules as they come off. And what I'm going to do now is to talk about a very different class of compounds and talk a little bit about the crystals themselves first, and then we'll get back to the reaction idea again. And this system is a system of borate dyes. And I'm going to show you, I think it's 4, maybe 5 different derivatives in which I'm going to change the alkyl group on the borate. And in one case, I will change some of the substituents on the dye molecule itself. But basically, the series of crystals I'm going to show you here are all very closely related. And some of them are going to undergo transformations where the alkyl group is transferred from the anion to the dye. And the product that's given off is in some cases going to be a gas and in other cases a liquid. And the consequences to the visual changes that we see in the crystal, depending on the phase of this byproduct, are really quite dramatic. All right, the first 2 slides I'm going to show you are of crystals that are quite stable. First of all, I'm pointing out that there's a sewing needle here, and that sewing needle is for calibration to give you an idea of what size these crystals are. They're all going to be in the range of about 1 millimeter. Some of them might be a little longer, some just a little bit shorter. But we're not talking about micron-sized crystals. We're talking about quite good-sized crystals that are easy to see with the eye. I'm showing you this particular slide as well as the next one because they show you that organic crystals can have many of the characteristics of inorganic crystals. Organic crystals are not always soft and gooey and green. Here are crystals that look like metals. They have sharp edges, they have bright faces that are just like a mirror, and you would normally associate those characteristics with inorganic crystals. In fact, they look more like that sewing needle than they do like what you might think organic crystals look like. But depending on the components of the crystal, it's possible to have even optical and electrical properties that are very similar to those of inorganic compounds. The same is true here. You might think you're looking at something like graphite or some kind of a metal. Very sharp edges, very deep colors. These are single crystals. They give single crystal diffraction patterns, but the edges are some of them are mirror-like. You can see the mirror reflectivity here, and features that look a lot like inorganic crystals. And this is often very typical of organic molecules that have large pi systems in them, large aromatic systems. All right, now we're still talking about the borate dyes, and here's the first instance where there's a hint of a crystal reaction taking place. These crystals are on a microscope slide under a fiber optic light source. There's no heating source here. And if you look carefully, you can see the edge of this crystal is starting to round, this lower left edge of the crystal. And underneath the crystal, you can see a phase boundary, and actually that's indicating a liquid that is underneath the crystal that's starting to form. And what's happening is the Br3 byproduct that's coming off here is a liquid, and it's actually dissolving the starting material. And so just a few minutes later, this was just a plain liquid, and it was not a melt. We didn't melt the crystal, we dissolved it. And here is another very unusual case in the same series of compounds. If we look carefully at the 2 crystals on the bottom, you can see little white specks that look like little white lights. What those white specks are actually indentations in the crystal. And the way those arose is that if you put these crystals in a fiber optic light source and look at them under a microscope, what happens is that on the surface, bubbles start to form, and they pop. And then another bubble forms and it pops. So the byproduct of this reaction is a gas. And as the gas forms, it causes the surface of the crystal to soften. And so pockets of gas develop. And then as the pressure builds up, it actually pops. And if you take the crystal off the microscope slide, after this has happened, it leaves these little pock marks. So crystal reactions like this are possible. They're unusual. I wouldn't have anticipated this, but there is a rationale for it after the fact. It's mainly a question of being observant. And in the same series of borate dyes here, we have some yellow crystals which are showing the first signs of reaction. Notice that some of the edges are a little bit dark, and the surface of the crystals are somewhat mottled. A few hours prior to this, these crystals were highly transparent and they had none of those effects of partial reaction showing at all. One of the reasons we were interested in these crystals is that they're a component of colored film for photography. And one of the questions was that this film tended to turn sort of a reddish color if it sat for a long time. And we were wondering if it was possibly a decomposition reaction of one of the dye components of the film. And photographic films are solids. So all of those color changes in photographic films are solid state reactions. So we let those crystals sit for a week or so, and after that time they had turned completely red. And so we think that this change from yellow to red is partly related to the poor quality of some of these colored films that we were looking at. And this is a pure and simple crystal phase transformation, and there's nothing exotic about it, and there's nothing really unusual about it. It's a very typical kind of a solid state reaction that we see often. And so looking at single crystal components of complex multi-component systems may give you some insight into unusual properties of those more complex systems. Okay, now I'm going to show you a series where we were actually not expecting to see a reaction at all. These compounds are dibenzoyl methane. And dibenzoyl methane compounds have been studied for years and years. This is a very large crystal, about 5 millimeters across, and they can be grown much larger than that. This is the stable form of dibenzoyl methane, and its crystal structure has been reported 3 times in the literature over a period of 20 years. And nowhere in those articles is there even a mention that there is any other crystal form of this compound. And we also were not looking for it. We were interested in dibenzoyl methane as the simplest member of a series of beta-diketomethyl compounds where we might be able to study tautomerism and proton hopping in the solid state. And so we wanted to start with the simplest member of the series and simply grow these crystals so we could get used to what they looked like and how to handle them. These stable dibenzoyl methane crystals are very easy to grow, large crystals out of many different organic solvents. But if during the process of letting a solution evaporate slowly, if you put that solution under the microscope and watch what happens, you'll see that you don't get these big crystals at first. The first thing you get are needles that look like this. They're big, they're well-shaped, they have clear, sharp faces on them. And this is a different polymorph of dibenzoyl methane. It's a metastable polymorph that had never been observed before. I'm sure it occurred almost every time that other form was grown out of solvent. It's just that if you set it aside and put it in the back of the hood and come back a day later, you miss all this interesting chemistry. Now, if you continue to watch this crystal as it sits in the beaker, what happens is, as the crystal is growing, all of a sudden, you see a diamond-shaped crystal grow at the tip of the needle. And just a few seconds later, down the side of the crystal, it goes bing, 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 and you get diamond-shaped crystals throughout the whole crystal, and it looks like rock candy. And so now that single crystal has transformed through a solution-mediated phase transformation into the stable form. We can also see this phase transformation when the crystals are not in solution but are out in the open, just sitting on a bench top. So if we remove the needles from solution before this has happened, we get crystals that look something like this. And the dark part is where the phase transformation has begun to take place. The clear part is the untransformed metastable crystal. And so I'm going to show you a sequence of slides here. Keep your eye on this clear part here and see how it changes over a period of time as we continuously take these pictures. We're taking them over a period of days here. Now on the two bottom small crystals, the product phase has moved further along the crystal needle axis. In the top one, there's been no change at all. Now the bottom two crystals are completely reacted and the top one still hasn't changed at all. And this is showing you again that crystal size, crystal quality, crystal width, crystal history has a lot to do with the initiation time at which a phase transformation begins or the rate at which it traverses the crystal. But then if we go back and take a picture maybe another week later, we find that the large crystal has finally transformed. But we don't know how to control that transformation. We don't know what initiates it and why it took place at a different time than the smaller crystals. Now, I'd like to suggest to you an experiment you could do to watch this solution-assisted change from a needle-shaped to a block-shaped crystal. You could do that experiment with dibenzoyl methane, and I think that you probably would see that change happen most of the time. But a simpler experiment to do, and one that might be a good experiment to do in undergraduate labs even, is where you take a saturated solution of glycine in water and just put a drop of that solution on a microscope slide. And then put it under a microscope and watch it. And what usually happens is that as the edges of that drop start to dry out, the needles of glycine start to grow into the center of the drop. But if you keep watching it, all of a sudden, those needles will transform into blocks. And you can see that solution-mediated phase transformation very clearly. The other way to watch the glycine crystal change is to put it in a small test tube. And the first crystals that come out just on sitting at room temperature probably will be the long needles. And then a half hour or so later, you won't have any needles, you'll have just the block-shaped crystals. Glycine has 3 crystal forms. Two of them are obtainable at room temperature out of water. The third form is hexagonal. It's shaped like a little hexagon, and you can get that crystal form out of acidic solutions, but that's a little trickier. Okay, now I'm going to talk to you about a crystal phase transformation, which involves an effect that we were not looking for, we didn't expect, and after we saw it, we still didn't believe it. And this involves crystals of this diphenyl azopalladium compound. This is an orthometallated compound, and it has a hexafluoroacetylacetonate ligand on it. Why did we look at this system? Well, I had a colleague at 3M. His name is Dr. Seidel, and he wanted me to do crystal structures for him, and I said, if you can find me a system that involves some interesting solid-state chemistry, then I'll do those crystal structures. Well, he found a wonderful solid-state reaction here. What he observed is that out of one kind of solvent, he could get yellow crystals. Out of another solvent, he would get red crystals, and these are polymorphs. And when he went to take the melting points of these compounds, he found that the yellow crystals turned red. And I thought, well, this is an interesting phenomenon. I'd like to take a look at it on a microscope slide, and I'd like to observe this color change myself. And what I saw, I did see the color change, but I saw something even more interesting, although I didn't understand it at first. As I started to heat these crystals up, when I had a lot of crystals on the microscope slide, as I heated them up, they started jumping. And some of them actually started flying off of the microscope table. And I just didn't believe what I was seeing. I couldn't imagine what was happening. And I also didn't tell anybody about it. And what I observed after that was that they turned red. And so I thought, I've observed this yellow to red transformation, and what happened in the meantime is just beyond me, and I just will forget about it. And so we decided to videotape this transformation. And in doing so, we still didn't see this other unusual step. But I'm going to show you a videotape in a minute here where you will see that what happens is the yellow form changes to an expanded form, and it actually pops. One end of the crystal will pop out. And after that happens, you get the red form. And it took us many, many viewings of that tape to realize that that was happening. The first 4 or 5 times we viewed it, we didn't even see that crystal expansion. So you're going to have to look very carefully at this tape. And as we play it, I'm going to try and focus your attention on the edges of the crystal that you want to watch so that you see the effect most fully. All right, let's start the next tape, please. Okay, now I understand there's going to be some audio in the background as I talk. So on occasion, I may be interfering with it. But what I'm showing you here on the bottom is the yellow crystal. Okay, now in this slide, on the bottom crystal, look at the top edge that's pointing up to the right and watch it very carefully, and don't take your eyes off it until something happens. Okay, you might have missed it. Back up the tape and watch again. In fact, if you want to, make a mark with a magic marker on your TV screen at that crystal edge and then rerun this tape. Now watch the lower edge of the top crystal. Again, I would take a magic marker and just make a line right on your TV screen. Otherwise, keep your eyes peeled very carefully on that bottom edge of the top crystal. And this is going to take maybe another 30 or 40 seconds before something happens, but I think it's worth the wait. If you watch carefully, I think you'll see that that edge is kind of creeping out. It's extending itself a little bit. But there still will be a catastrophic event take place in just a minute here. While you're watching that, I'll point out that the kind of blue and pink colors you see here are artifacts. The crystals were really very yellow and transparent to start with. And when we're done, they're actually going to be red, although the color change to red is hard to see in this frame, and it will be easier to see subsequently in the other frames that I'm going to show you. The temperatures that we're working at here are now about 95 degrees, and this is another example where one crystal underwent this transformation at a very different temperature than the other crystal. But I think they're within about 5 degrees of each other. Don't go to sleep now. This is worth watching if you pay attention. There it goes. If you missed that, you really need to back this tape up and watch it again because it's worth seeing. Oh, someone backed the tape up. Let's see it go again. Now we're going to watch that top crystal. There it goes. So one end of each of those crystals expanded like popcorn, and consistently the expansion is 10% of the length of the crystal, and it always occurs at one end of the crystal and not the other, even though the starting material and the product crystals are both centric. So this effect we don't understand at all. We don't know why the stress is building up and being relieved just at one end of the crystal. After the expansion takes place, there is a color change that usually starts at the opposite end from the expansion and then runs down the crystal almost like a liquid. But it's not too clear in this particular slide. Although I think at this point in time, the bottom crystal has turned completely red. And we'll wait just a minute, and then this will move on to, I'm going to show you examples of this crystal expansion with crystals that are thinner and fatter. All right, now this one, we're heating the crystals just on the bottom. So what's going to happen is the bottom is going to expand and the top isn't. And it shoots the crystal right off the stage. We'll repeat that. So you can, this is the origin of the crystal jumping effect that I had observed earlier. Okay, one jumps, and at a slightly different temperature, the other one will just fly away. There it goes. And notice the other two longer crystals haven't changed at all yet. These crystals are a little harder to see. They've already undergone the expansion phase. The white parts that you're looking at are just reflections, so that's not really relevant to what we're looking at or trying to understand here. What you're going to see here, if you watch carefully, is that the product phase will come in and it will look either dark purple or black in this particular frame. And if you can kind of watch one crystal at a time, it will look almost like a liquid running down the crystal. So these are basically unidirectional phase changes in most of the crystals we look at. So they're anisotropic, and this is one of the interesting parameters of solid state chemistry that you don't have with solution chemistry, and that parameter is direction. But in many cases, you have reaction directionality in crystals, and we're seeing an example of that here. Again, these crystals are about 1 millimeter long, maybe 2 for the longer ones. This is a very thick crystal compared to the ones I've showed you before. It's probably several millimeters long, and this is the only case that I remember where a color change starts before the expansion. Watch the bottom right corner of this crystal. It will turn dark in a few minutes, and when the expansion takes place, there, the crystal jumps. But if you measure the length of the crystal before and after it jumps, you'll see that it's expanded about 10% of the length of the original crystal. Oh, I guess we're going to run it again here, huh? Okay, the color change is just starting. And there, the crystal has jumped, and it hasn't changed color yet, except in that one little region. I think you'll see there will be another region where the color change will start, but in a minute, the whole crystal will start to turn red. And that red color will move down the crystal. This one, the color was initiated at both ends. But the liquid-like motion is showing you that these are cooperative transformations, like a deck of cards falling over. You're getting molecules influencing the neighboring molecules. All right, now this one is an extremely thin crystal. Watch the top right corner. Not the piece that's off the screen, but the little edge that's about 3/4 of the way up the screen. And again, take your magic marker if you have one and just make a mark there. And it jumped. The other end of the crystal didn't change at all, but there was an enormous change in length at that point. And in this crystal, since it was so thin, there are fracture lines and cracks in it, and you'll see the color change initiated at several different points of the crystal. But you will also be able to see very clearly this liquid-like effect as the color change takes place after the expansion. And I assure you these crystals are not liquid. You can pick them up and take them off the microscope stage at any time, and the transformation will stop. The color won't change any further. The expansion will not proceed further. And then you put them back on the stage, and the color change will initiate again. Okay, I think that tape is done. That crystal's completely changed. So what I'd like to give you is a rationale for what's happening. We don't understand the mechanism in detail, but we do know the crystal structure before and after the phase transformation takes place, the complete phase transformation. What we're starting with is the picture on the left. This is a crystal structure, a view of the crystal structure of the yellow crystal. And I'm going to show you with my hands how I think the phase transformation takes place here. The crystal structure on the left has the molecules arranged sort of like this. So they're head to head. The product crystal has the molecules interleaved like this. And the crystal expansion actually takes place in this direction of the physical, the macroscopic crystal. So there's some sense that it might be a dislocation that interleaves the molecules suddenly, and then there's extension, the length of the crystal in the direction at which we have actually increased the molecular number of molecules in that direction. Now, why isn't that enough of an explanation? Part of the problem is the starting material, which is yellow, has the phenyl rings twisted slightly relative to one another. We think the red color occurs when that flattens out because the product red crystals are much flatter than the starting material. So we think that's the origin of the color change. But notice when the expansion takes place, you're still in the yellow form. So it's almost as if this takes place, and then after that's happened, the phenyl rings become planar. So they might initiate a change down the length of that axis where they flip over one after another, but we don't know that. It's very hard to know that. We've done a lot of studies on the intermediate form of the expanded yellow crystal, and all we can learn is that it looks like a slightly disordered yellow crystal. We don't see any new phases. We don't see any amorphous material. So this is a real puzzle, but this is the kind of thing that happens with organic crystal chemistry. A lot of the phenomena have just not been studied yet, and being observant and being curious often has a very big payoff. Okay, in the next slide, I'm going to show you another, what I think was a curiosity. And that is, if we take, there are some samples which we can take as plain, dry crystalline solids and grind them together and get a new co-crystal, a new compound. And you can't see the structures very well here. I think you can see the samples better. But on the left, I have paranitroaniline, which is yellow. On the right is paranitropyridine N oxide, which is light yellow. And when you grind these two samples together, you get a 1-to-1 co-crystal, which happens to be dark red. And the dark red color comes from charge transfer interactions. But the driving force for the change, when you simply mix these two solids together, is the formation of strong hydrogen bonds in the product. You can get this same crystal form by growing the red crystals out of solution. So you put the two yellow solids in solution and let it crystallize, and what you get out are red crystals. And these red crystals contain both of the components, but they're hydrogen bonded together in a new way. It's really a new compound. It has new melting point, new infrared spectrum, different colors, different optical properties, different electrical properties. And most of us think that when you mix solids together, nothing will happen. And in fact, the way we found out about this was we wanted to get an infrared spectrum of a mixture of these two compounds, and we couldn't. Whenever we ground the solids together with KBr or NuGel, we always got a spectrum of the co-crystal. And it took us a little while to figure out what was happening here. And here's another example. This one's a little clearer. On the right is meta-aminophenol. It's white. On the left is paranitropyridine N oxide again. And in the middle is the dark, dark red co-crystal of the two. And this forms very easily. This is an experiment that you could do in the lab, except I'd like to point out that the compounds are carcinogenic. So you want to work with small amounts in a mortar and pestle, and preferably in the hood. But the reaction goes very quickly. After 3 or 4 minutes, you see a slight red change if you just keep grinding and grinding. And if you grind nice and hard, after 5 or 10 minutes, it will be this really, really deep red color. So this is a good example if you don't believe me. Good one to try yourself. Now, you don't even have to grind some of these samples. What I have here, although the structures are backwards, but what I have in the Petri dish on the left is paranitropyridine N oxide. And on the right, I have paranitroaniline, which is yellow. And around the edges, you can see something that's red. And the red color develops in this Petri dish if you simply cover it and let it sit on the benchtop for a while. And what happens is that paranitropyridine and oxide, which has a reasonable vapor pressure, simply sublimes and finds its way over to the paranitroaniline, and when it does so, co-crystals form. So this is a gas-solid reaction. And I'll show you on the next slide. I'm going to focus in on the red region here to see what that looks like. Here are the yellow crystals of paranitroaniline. They're great big large crystals. And you can see the surface is very mottled, which is typical of a crystal that's undergoing a reaction. It might actually be subliming a little bit itself. But the red crystals that you see here are the co-crystals that have formed from the gas-solid reaction taking place just at room temperature. So this is a very nice, convenient way to make new materials. In fact, the grinding experiment can be done with more than 2 different compounds. You might be able to mix different stoichiometries together and get non-stoichiometric solids, or mix together 3 or 4 things and get compounds which you might not get out of solution at all. And the other time that solid state grinding might be useful is that if your 2 components are very different, have very different solubilities, what happens when you put them in solution is if one is much, much less soluble, it will just precipitate out, and then you won't get co-crystals. So if you want to grow co-crystals out of solution, you need to try and find a solvent where they have nearly equal solubilities, and then the co-crystal will form. But if you do the solid state mixing method, you don't need to worry about solvent balancing. In fact, you might want to make your co-crystals in the solid state, and having made them, then find a solvent for the co-crystal and do a recrystallization to get a nice crystal form. Because the solubility of that co-crystal mixture will be quite different than the solubility of the starting materials. Okay, a final example that I'd like to show you here is a real reaction. That is, it involves changing sigma bonds and forming a brand new compound. This reaction was discovered by one of my students, and I really didn't believe it, and it is extremely overcharacterized. So I can assure you that we now know exactly what's happening. We don't know the mechanism, but we do know that we get this product, and that is without question. So what we have here is a series of solid state reactions. We're going to start with 2 different carboxylic acids. One of them has an amine group, that's para-aminobenzoic acid. The other acid reagent has 2 nitro groups and a parachloro group, and that parachloro group is activated by those nitro groups. The first thing we do is simply grind those 2 acids together. And when we do that, we get a new co-crystal, just like the reactions I showed you just a minute ago. So on the right, we have a heterodimer. We have the typical co-crystal hydrogen-bonded dimer, but we have one acid on one side of the dimer and a different acid on the other side of the dimer. And now if we heat that sample up, it does something different than what I've shown you on the slide, actually. What it does is go to another polymorph. That polymorph was just recently discovered by one of the students in my lab, by Gandhara Ranawaki, who's been trying to work out the details of this reaction. So the other polymorph of 3 is still a diacid co-crystal. When that polymorph is heated, however, what happens is this new compound forms. So compound number 4 forms, which is an entirely new molecule. And if you look carefully at it, what you formed is a new nitrogen-carbon bond, and the chlorine has been displaced. So we've done a nucleophilic aromatic substitution reaction in the solid state. This is a 3-step solid state reaction. This molecule will form quite easily in solution from those components. So in this case, we're not getting a new compound, although there are instances where solid state reactions will give you new compounds or new stereoisomers. But in this case, we're getting a reaction which we really did not anticipate. We now know the crystal structures of polymorph 3 and of polymorph, the next polymorph, higher temperature polymorph. And even knowing those crystal structures, we still could not have anticipated that this reaction would take place, because the crystal structures of the reagents do not mimic a transition state that is reasonable for this product. So there must be enormous molecular motions taking place in order to get this product in the solid state. And I'd like to show you just a simple experiment that my student did to convince me that this reaction was taking place, because I really was not a believer at first. And so what she did was simply take some of the starting materials, the starting co-crystal, that is the diacid co-crystal, and she put it on a heated microscope slide. And over the top of the slide, she put an inverted Petri dish with a drop of silver nitrate. And she decided she could do a silver chloride test this way, because if that nucleophilic substitution reaction was taking place, then one of the byproducts is HCl. And so she simply heated up the sample here, HCl came pouring off, and we collected silver chloride in that drop. And so when I saw that experiment, I thought maybe she was on the right track. And she went through extensive further characterization to prove to me that that's actually what happened. So you can do some useful syntheses of compounds by making and breaking sigma bonds in the solid state as well. It's hard to anticipate when that's going to happen, however, but it's something that you should keep an eye out for. Again, being observant, being curious, and believing your eyes and believing your data, even when it seems completely unlikely. This slide is what I think represents what happens when a solid state phase transformation takes place. When my daughter was about 4 years old, we were sitting on the floor together, and I had ORTEP diagrams spread out all over the floor, and this is her interpretation of my ORTEP diagram. And it shows a molecule with a lot of energy undergoing a lot of motion, and is just obviously ready to react, I would say. And it's sort of similar to this slide, which says, the caption is, there are times when I wish we had a somewhat stronger organization. So I see this as a phase transformation taking place prior to crystal nucleation of a new product phase. And what we would like to see as the crystal change takes place is this lovely transformation from one kind of molecule to another kind of molecule, possibly from one polymorph to another as the ducts rearrange themselves. This is showing an actual change from one type of molecule to another. But I think this is a very nice schematic diagram. This is an Escher drawing of how I view phase transformations in the solid state. And I'm going to now show you I'm going to give you some acknowledgments and show you some of the literature references to this work. Okay, so there are a lot of people that I'd like to acknowledge for this work. It represents many years of experimental chemistry. The cyanoxanol chemistry was done in collaboration with Professor Joel Bernstein, who did a sabbatical in our laboratory for a year. It was also done in conjunction with Dr. Derek Cash from 3M, Professor Bill Gleason, and Ruth Johnson. Ruth is a expert crystal grower. She's very observant, very careful, and really has a green thumb when it comes to crystal growth. The borate dye chemistry was done with Dr. Brian Holmes and Ruth Johnson. Dibenzoyl methane chemistry was done with several of the students, my students, graduate students here at the University of Minnesota. The palladium crystal expansion was done with Dr. Alan Seidel at 3M. All of the students in my research group are involved in solid-state grinding now that we know how useful it is, but the two students who did the most work originally and showed us how useful it would be are Dr. Dan Adsman and Dr. Gail Frankenbach. The nucleophilic aromatic substitution reaction again was studied by several people in our laboratory, and Gandhara Ranawaki is currently finishing up that study, and we're trying to make as much sense out of that as we can. And I would especially like to thank the people from the pharmacy department here at the University of Minnesota, who provided us with that very interesting dehydration tape that showed the crystals smoking. And I'll put up just for a few minutes the references here. Let's see if I can get them on the screen. I'm going to hold this for a few minutes for those of you who would really like to copy these down, and then I'll move it up so you can see the bottom references. The first one is the crystal expansion, as is the second one. The second reference is more of a general discussion and review of that particular reaction. This reference is for cyanine oxygenol dyes. This reference is for the cyanine dyes and the borate dye chemistry. This reference is to the dibenzoyl methane phase transformations that I talked about. And the final reference, although not yet published, is a reference to Professor David Grant. And I suggest that you could talk with him or me about details of this, or perhaps just watch the literature. I think in the near future this will also be published. And I'd like to thank you all very much for your attention and for your time today. Thank you.